1 second. I think my iPad is on the wrong Wi-Fi. All right. Let's go back to where we were. And I think the last example we talked about was here. And we were talking about the difference in kinetic and thermodynamic control. And the main difference is the temperature and the energy that's available to access each product. And so when we were talking about this conjugated diene, we also talked about the fact that either one of these could react. So here or here, but I think the example that we worked on, it was the alkene that was highlighted in red that we did first. And the key to the reaction is here, right? Whichever alkene you choose, the key to understanding the reaction is actually knowing that the intermediate is always going to be the same. It's going to be an allylic carbocation. So that plus charge has to be adjacent to where that second alkene is. It's an allylic cation every single time. So if you know that part, then that helps with the product formation, right? Because now we can talk about the two different product pathways, right? Where you have here the 1,2 pathway, right? Where the bromine just attacks directly. And I'll just number that out here. And then over here, you have the 1,4 pathway, right? Where the bromine doesn't attack directly. It actually, the way we talked about it, it actually attacks like the resonance form of that allylic cation, which is still an allylic cation, that the plus charge is here, and then the alkene is here, right? So those are your two product pathways. Both products come from the same intermediate, and that's the key to the reaction, right? If you that doesn't change. So once you get to that carbocation, that allylic carbocation intermediate, then both of your products come from there, right? So I think the question was, for this first example, to draw the major amount of products under kinetic control, right? So kinetic control, this will be major because it's faster. Recording. Thermodynamic control, the minor product would be the 1,4 product. And then if we heat it up to 37, and we looking at the same alkene, it's going to flip flop. The minor is going to become the major, and vice versa, because at 37, the 1,4 product will predominate, right? And then the 1,2 product becomes minor. All right, so the way we explained it was looking at these two reaction energy diagrams here, right? And we talked about how at low temperature, everything is irreversible. So once the intermediate gets converted into product, that's it, right? So even if the product is a higher energy product, like the 1,2 in this particular case, it doesn't matter. That's the fastest product form. So it's the kinetic product. So that's the once you form it, it's irreversible, right? And it's not like you don't form some of the other product, but the lower activation energy for that 1,2 product means that you're going to have more of that under these conditions, which are typically low temperature conditions. Then if you increase the temperature, you set up an equilibrium. So the intermediate is here, and the intermediate can either go to the 1,2 product or the 1,4 product. And I think up here we had P1 was the 1,2 product, and then P2 was the 1,4 product. So over here, this was 1,4, and then this was 1,2, right? But at higher temperature, that less stable product, higher energy product can actually go back, decompose and go back to the intermediate. And that's what we talked about in this example here. We didn't finish it. Well, we did the first one, but we didn't do the second one. So that's what we're going to do today. But I'm just kind of recapping where we left off on Friday. So the 1,2 product, if it's higher in energy, it doesn't matter. At higher temperatures, there's more energy available. So it can actually go back, traverse back to the intermediate, because under these conditions, everything is reversible. So you can go from product back to intermediate, and then you can take that intermediate, because there's more energy, you can get over the activation energy hump here, right? And then get eventually to your more stable product. So that's how we are able to, at higher temperatures, take P1 and turn it into P2, because it can go from P1 back to intermediate, and then from intermediate to P2. All right. Any questions about that? Did that kind of clarify a little bit, Danielle?
Yeah, it does.
Okay. Let's do another example. I want to do the other alkene, the blue one, and we're gonna do that example, and then we'll come back to the. We're not gonna jump into cycle addition just yet, but we're gonna do the other alkene, and maybe that'll help it also crystallize. So let me just take take that and put it here. Man, today is the 24th. All right, so let's talk about this in terms of the other alkene reactant. So this one, if that alkene, finish that other diene. I don't want to say alkene.
Still right. Then there are the 3-1. CHEM.
All right, so if this is my diene, but this is the alkene that's reacting, I take that and react it with HBr. What's going to happen?
The alkene is going to become it's going to get deprotonated.
All right, so it'll attack like so. Now the question is, and this is the key to understanding this reaction. What is the intermediate? What does the intermediate look like after that happens? After that alkene, the electrons in that pi bond attack HBr, where's the plus charge going to be, and where's the hydrogen going to be? That's the question. If you can answer that, then the rest of the problem is just academic, right? It's not a mystery if you can get to the intermediate. So what does the intermediate look like?
The plus is going to be to what the alkene that got detached was, but at that the third carbon.
Mm-hmm. So you said, let me see if I can. You're saying it's going to be right here?
Yes.
Yeah, and that's the key to the problem. This is, let me fix that up. All right, so here's my double bond. And then this is an allylic cation, right? Every time you do this reaction of a conjugated diene with HX, the intermediate is always the same, right? The plus charge could have been here, but for this particular reaction, since it's a conjugated diene, it has to be allylic so that you can stabilize it by resonance, right? So that's why that's there. So if I just take that and then I have a bromine here, right? If it just attacks directly, and then again, let's number this too, because let me make the 1, 2, and 1, 4 make sense. This is 1, 2, that's 3, that's 4, right? So if it attacks directly at 2, that's going to give me this product. Now, what does the resonance form for that look like? That's going to help me to know what the 1,4 product is going to be.
Let me see, the proton, the plus charge is going to be on the 4
Okay.
carbon,
Okay. I agree.
and the double bond is going to be in between the 3 and the 2, the
Good.
third and second carbon.
Good. Good. So I can do that, right? And then I'll have this as a resonance form like that. And then that can react with bromine. Let me move that over some. Right, so that can react with bromine, and then we end up with this product. Here. Like so. Anybody not see that? So if the other alkene reacts, which it can, because there's no impediment to it reacting, both can react. This is the intermediate right here. And then these are the 2 products. This is the 1, 2 product, and then this is the 1, 4 product. Now, what's going to determine which one is major at 0? What's going to determine that? Oh, let me not say it like that. What do we call that product if the reaction is done at 0? Which one is going to be major? That's how.
The kinetic, so the least stable.
Okay, so would
So
that
wouldn't
be
it be
1, 2,
1, 2?
Yeah. So this product right here, I'll just copy it. That's major at 0. Simply because it, again, is more accessible. That cation is more accessible. So at low temperatures, again, the fastest form product is going to predominate. I think I said it in the video about like these 2 processes being like the difference in coming home from work or class and having access to a bologna or whatever you like to eat, something quick, a sandwich versus a full meal, like, you know, a pot of beans, fried chicken, cornbread, whatever. If you come home and you're famished and you don't have time to cook and you're beat and tired from working all day, you're not going to try to cook a full meal. You're going to eat whatever's in front of you. So you'll make a sandwich, or you might warm up something that's in the fridge or something like that. That's the equivalent of accessing that kinetic product. There's not enough energy to do a whole lot, but the energy that's present, you do what you can. And so that's why reacting at the 2 position, but a cation is, that gives you that 1, 2 product. It's the quickest thing that you can get to. And then the 1, 4 product, under kinetic conditions, which is low temperature conditions, H2. Right. Under kinetic conditions, the 1,4 product is going to be slower, right? So that's going to be your minor product. Right. And then if you do it at 37, it's going to flip-flop. The minor product is going to become the major product because there's more energy available to access it. And then the major product at 0 will be the minor product at higher temperatures. Right. But this is all, again, everything is predicated on formation of that intermediate. And it's always the same type of intermediate. It's an allylic cation. It will never be anything else. Once you get to that, then you can figure out what your other products are. All right. So if we go back up to here and we think about these two, this it being the kinetic product from the blue alkene that we just looked at. Can y'all see that? So that's the kinetic product. Same thing. The 1,2 product is right here. How do I get from that back to the intermediate? So let's say I leave this, I set this reaction up, I go to lunch, and before I leave, I pack it down with ice. If I'm running it at 0, I pack it down with ice, and then I go to lunch, take a long lunch. By the time I come back, it's a little bit above room temperature. How do I show the kinetic going back to the intermediate, and then the intermediate going to that 1,4 product? How do I show that?
Oh,
So I have it right here. How do I get from here to here?
Bromine gets kicked out and becomes a carbocation.
Say that again. So you said kick out bromine.
Yes.
Okay, spontaneously, just let it go, let it fly.
Yeah. Well,
Yes.
yes.
No second guess it. Yes, we've seen this, right? SN1 reactions and E1 reactions do that all the time. Is that right? The leaving group leaves spontaneously. There's no catalyst. There's no external force. If it's a stabilized cation, leaving group is going to leave spontaneously. So yes, the answer is yes, just kick it out. So we show that like this, right? So this is that. And we just show an arrow with the carbon bromine bond breaking. Is that right?
yeah.
Mm-hmm. And that'll get us to here. Now, how do I get from here to here? This is the other product.
Resonance. Wait, I think.
Okay, I'm
Yes.
with you. You can do resonance. I agree, to get you to a new allylic carbocation. I agree with that. I do agree with that. But now I need to go from that to that. So how do I do it? I have my bromine right there. Is that right?
Yeah, you just added where the proton, where the plus is, right?
So I just attack it. But the point of all of this is that if you're working under kinetic conditions and you warm the reaction mixture up to the point where you can convert those conditions from kinetic to thermodynamic, your kinetic products can be converted into the thermodynamic product. That's why we're looking at this particular example right here, right?
Dr. Russell, I have a question.
Go right ahead.
So I thought the kinetic was the irreversible one.
It is. But if you warm the temperature up, you add more energy to the system. And so that allows for reversibility. When the energy goes up, think about it like this, right? If the goal of chemistry is to go from less stable to more stable, and you have a product that's a low stability product, but you introduce conditions or opportunity to go from that to a more stable product, is going to happen. Right. So under kinetic conditions, the idea is that the product you get may be less stable than the thermodynamic product. But if you introduce more energy, that product with the less stable product will much rather be the thermodynamic product. So it can interconvert. So you can induce reversibility, if that makes sense to you.
Yeah, that makes sense. And then I think my other question was, I think the way I kind of get now, like I think my first question on the test was thermodynamic, and then
Mhm.
they asked me a kinetic. So I didn't assume I was going from one to the other, like from the next set of questions. I didn't assume we were starting out and then the intermediate was gonna go back and form a new one for my higher temperature. How are we supposed to know that it's gonna revert back to the
Okay,
more
that's a
stable
good
product?
question.
Just from looking at it, is a kinetic always
What you're looking at is the temperature. So the temperature is going to dictate whether something is kinetic or thermodynamic, right? If it's at low temperature, then the reaction is going to be assumed to be under kinetic conditions. For this reaction, addition of HX to a conjugated diene. If it's low temperature, you assume that it's under kinetic conditions. If it's at higher temperatures, then you assume it's under thermodynamic conditions. Did that answer your question?
right, but then I guess so then it would say HBr, and then it would say like 2 degrees Celsius.
Yeah.
And then
Like here, right?
you predict the product kinetic. Yeah.
Mm-hmm. So the conditions have
But
to be given.
I think the question was, right, so the tallest one, well, so the one on the top is a lower temperature, so it's
Yes.
gonna be kinetic, and so
Yes.
it will produce the least stable.
Yes. In theory, yes.
But I thought in the test, I thought that in theory, but then how would I know, okay, well, the product is actually gonna be major if it reverts?
So I think the question you're asking is, it goes back to what the intermediate looks like. So let's go back to here, right? For this reaction, this is the intermediate. It's the allylic cation. That intermediate, both products come from it, right? So depending on the conditions, if it's low temperature, again, bromine is just going to attack where the plus charge is, because that's the fastest route to get into the product. So that gives you this 1,2 product right here. If you increase the temperature, then you open up the other pathway where you can get to this intermediate, right? Which is the resonance form of the allylic cation, and then bromine can attack here. Oh, wrong pen. Like that. So everything is predicated on the intermediate getting converted into product. And if it's low temperature, it's going to be the 1,2. Not saying you don't get any 1,4, because you will, but you won't get as much. If you increase the temperature, it's going to be the 1,4 product that predominates, and you'll get less of the 1,2 product. So I think maybe that might be the disconnect, is that it's all one or all the other. And that's not the case. It's always one of them is major, one of them is minor, if that makes sense.
Yeah, it does. So it wouldn't be wrong if if let's say it's kinetic and I draw both 1, 2, 1, 4 as the isomers or like different racemic, like, right? It wouldn't be wrong to draw it, and then if I label the more, right, if it's kinetic, it would be the minor, that's my major product. If that makes
Yes.
sense, right? It would be the least stable by major product.
Yes.
And then for the other, it would be the most stable or thermodynamic stable. But, and that will always happen. So as far as like predicting the carbocation,
Mhm.
it's based off of the numbering of carbon. Okay.
Yeah, but the way to identify that immediately is to always make it allylic. That way, you really don't. I mean, you really don't have to. You can predict it based on where the other double bond is, right? So just like right here, the other alkene was here, so that's automatically it's a given that my plus charge is going to be right here next door to that second alkene. If we were reacting this alkene right here, it's a given that the plus charge is going to be right here, right? Because it's next door to this alkene. So it's all the intermediate is always going to be allylic, no matter which double bond you use. The positive charge is going to be in an allylic position to the other alkene.
Okay, that makes sense.
It sounds like this is what I'm thinking. What I'm going to do is I'm going to take those, well, take another set of problems similar to the ones that were on the exam. I'm just going to make that into a separate assignment. And then I'll give you all another opportunity, another crack at that. It'll probably be Wednesday before I can get around to doing it, but I'll make an announcement and I'll give y'all another crack at that section. All right.
Okay, that's good.
It seems like there's a little bit more clarity today. I think the reaction part was not the issue. It's the understanding of the mechanistic side, like the the energetics and the thermodynamics. I think that's the disconnect. But I think we are a little more clear today than we were on Friday. Are any other questions? I think that's another problem here that we're working on. Are any other questions about anything from this section? All right, so I want to shift gears then. And I want to introduce the cycloaddition section. This is a bit more mechanistically, it's a little bit more involved than this previous reaction. But again, you know, think back to when we first started this section, we're talking about conjugated dienes, right? And we talked about conjugation first, and then we talked about conjugated dienes and how they are special because the two central carbons are attracted to each other, so they shorten the bond length and they make all four of those orbitals overlap. So the way a conjugated diene reacts is different than just how a regular alkene reacts. So let's jump into this next section dealing with cycloaddition, and I'm gonna just kind of introduce you to that first, and then we'll go from there. So we're gonna look at cycloaddition. So the cyclo part means I'm making a ring. And then the addition part is I'm adding two components. Right. So there are a lot of different types of cycloadditions. I'll say that up front, but for the scope of this class, we're going to look at the 4 + 2 cycloaddition. Right? And I think I gave you an example, but we didn't really go that deep into it. This is also called the Diels-Alder cycloaddition. Right, so typically you'll take a conjugated diene, right, and you're going to react that with just an well, not always just an alkene, but I'm gonna make this here. I'm gonna use that because I want to also talk about some of the other properties of the reaction. Right, there's a lot of different. It's a very nuanced reaction, and it's endothermic, so you have to do it. You have to heat it up to get it to go. Right, but here. Right, the reaction is, I think I mentioned this before, I'll mention it again because it bears repeating, it's pericyclic. What that means is that the electrons move in a circuit. Right, only these 6 atoms are involved in the transfer of electrons. So that's what we mean by pericyclic. Those 6 atoms only together, right? Those are the only atoms where electrons are shared across, right? So we got that. And then we take this pi bond and push it here. Like that. And then this pi bond gets shifted, excuse me, down to here. All right. So what you end up doing is making a bond here. Right. You're going to make 2 new bonds and you're going to make 2 new sigma bonds and a new pi bond. So this is to here. Here, you're going to have a bond between these 2 carbons. Then you'll have a new pi bond here. Right, so my product is going to look like this. I get a 6-member ring. This is always the outcome. A 6-member cyclohexene derivative, right? Always. My new pi bond is here. And then my 2 new sigma bonds are here and here. And then, of course, I have substituents over here. So I'm going to show that too, right? So these are, I'm going to draw them on a wedge. Those 2 methyl groups here. Right, both of them are wedged. That's on purpose, and I'll explain that. So this is the 4 pi system is over here. That's the diene. And then over here, this is my 2 pi system, and we call that the dienophile or lover of dienes. So dienophile and diene. That's what a 4+2 cycloaddition involves, right? The four part is the diene, the +2 part is the dienophile. But every time you react those 2 things together, you're going to get a 6-member ring. This is the outcome. Now it may be a 6-member ring connected or built into another, system. It may be a larger system, but when that 4 pi, 2 pi come together, that's what you get. You get a 6-member ring, no matter what other substituents are attached to both your diene or your dienophile. It doesn't matter. All right, questions about that? Right,
No.
so let me ask this question from Organic One. What is the stereochemistry of that dienophile? Is it cis or trans?
That's the dienophile.
Say it again.
It looks cis.
Yeah, it's cis, right? Why do you say that? What makes an alkene cis?
It's when the stereochemistry is on the same plane. Or,
Yes. So both of those, you see both methyl groups that are bonded to the carbons in the alkene, they're both on the same side with each other. So that's right. So when you do a reaction like this, we say that the reaction is, I'm gonna write it over here, stereospecific. What that means is the stereochemistry of the dienophile is maintained. Right? So if I start with a cis alkene or cis dienophile in the product, the groups that were on that alkene are also going to be cis, right? So we say that this is cis. Over here, they're also going to be cis. That's one of the key characteristics of this reaction is that stereospecificity, right? You start with a cis alkene, then in the product, those two groups still have to be cis. What if I started with an alkene like this, and then I reacted that with a diene? Right, the mechanism never changes. I'm always going to do this here and here, and sometimes it helps to number. When I've taught this in the past, I've always numbered the carbons. So this is 1, 2, 3, 4. This is 5, and that's 6. So when I react those two together, I'm going to get a 6-membered ring like this. The alkene, the pi bond gets shifted here, but over here, these groups are trans because the alkene itself is, well, the dienophile is trans. Right? Yes, no?
With practice, yes.
Okay. Well, that's fair. That's fair. It's going to take some practice. I agree. And we got a lot of problems that we're going to work through to practice it. So yes. All right. Let's talk in the last 7 minutes about some molecular orbital theory. And that's going to help us understand other things about this reaction. Right. So molecular orbital theory is it's a type of bonding theory, kind of like valence theory, but instead of atomic orbitals combining to make either hybrids or combining to like in valence theory, where you just combine the orbitals and overlap valence shells, molecular orbital theory is a little bit more complex, and you use it to kind of explain more complicated reaction types like cycloadditions and things like that. So if I take a diene like this, right? And remember, we talked about the fact that it's conjugated. Those p orbitals are overlapping, right? So the p orbitals here are overlapping, being pulled together, and then that makes all these p orbitals overlap, like it's like a system. So molecular orbital theory says that if I have 4 atomic orbitals, because each one of these p orbitals is an atomic orbital, then that's going to give me 4 molecular orbitals. It's just like hybridization. The number of orbitals, the number of mixed orbitals you get is the same as the number that you add together. So if I got 4 atomic orbitals and I'm mixing them together, I'm going to get 4 molecular orbitals. What that means in kind of basic terms is that those 4 orbitals overlapping can combine 4 different waves, right? So let me just show that. So I'm gonna get, so I have here, that's one set of molecular orbitals. This is the other set. This is the other set. And this is the other set. Right? So the other part of MO theory is that goes past valence theory is what we call the particle wave duality. Right? And what that basically says is that electrons can behave both as particles and as waves. Right? They can do both. So that particle wave duality is going to help us with the other part of this molecular orbital discussion, right? How many of you have had physics? By show of hands, you can just use the hands up feature if you can find it. Okay. Only 2 people. Wow. So Danielle or Asia or Farrier, somebody answer this question. When you studied like waves, sine waves, okay, when you study waves, if a wave never passes through 0, does the sign change? The sign of the wave?
No.
Right. Because remember, the wave can be like this, right? This is what we're talking about. So that's one time passing through 0. And anytime the wave passes through 0, we call that a node. Is that right? But if the wave never passes through 0, and then of course here it goes from what? From positive to negative. Is that right?
Yeah.
But the bottom wave never passes through 0. So it's all positive all the way across. Right. So this is, I can use this actually. So every time the wave increases in energy, is that right? It's going to pass through 0 more times because the frequency is going to go up. Is that right?
It sounds right. I took it like a year ago.
Thank you for your honesty. Right, it's true. So if I go up to the next energy level, that wave is going to pass through 0 twice. And then if I go up again, that wave is going to pass through 0 3 times. I need to shorten that wave. 1, 2. That's too many times. Here, 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 like so. Right? So every time the wave increases in energy, well, the energy increases, the frequency increases. And every time the frequency increases, that means the wave passes through 0 more times. So over here, the way I apply the wave part to the particle part is that each one of these orbitals is in a particular energy level. So this is energy increasing, going up. Right? And then at the lowest energy level, the wave never passes through 0. And then here, the wave passes through 0 once. And then here it passes through twice. And then here it passes through 3 times. So we got 3 nodes here. All right. The way to think about this, so we got 2 more things to add in to this MO diagram. Right. Everybody, how many of you remember from organic 1 that a p orbital has a node, and it can be positive on the top and negative on one side, or where we show it is shaded on one side and unshaded on the other side? Anybody remember that for p orbitals?
Slightly.
Yes.
All right. So how that applies here is that in that first energy level, since the sign never changes, the signs of the orbitals won't change. Right. Then you go to the next energy level. What do you think happens when that wave passes through zero? Do you think there's going to be a sign change? It should be, right? Because the wave passing through zero changes the sign of the equation. So that's how we're going to look at those. And then the next energy level, this is shaded. The sign changes here. And then here it changes back. What about the top? What do you think? Just logically.
Shaded on the top, shaded on the bottom, shaded on the top, shaded on the bottom.
So it should alternate, right? So this is right here, what we just constructed based on what we know about waves and what we know about particles. We just constructed what's called a molecular orbital diagram, or MO diagram, for a 4-pi system. We can't do this if it's not conjugated. The only reason this exists is because of that conjugation. So all 4 of those orbitals get to be counted as one unit, as opposed to 2 separate units of 2 orbitals each. Without conjugation, you can't do this, right? The only other part, how many electrons are here in this 4-pi system? Anybody? I got 1 electron in each of these p orbitals. So how many is that total?
Did you mean, so is it 4?
4. Right, this is a 4-pi system. Right, what that means is that there are 4 pi electrons. So here, these orbitals, you fill them up just like you would an orbital for an atom, right? A set of orbitals for any given atom, right? Like the 1s, 2s, 2p, 3s, 3p, 4s, 3d, so on and so forth. So I'm going to fill this up, and then I want to fill up this one. And now there are my 4 electrons, right? So that's a MO diagram for a 4-pi system. We're going to pick this up on Wednesday, so don't panic. And I'm going to send you a video dealing with cycloaddition this afternoon. So check that out. And then when we come back Wednesday, it'll be a more spirited discussion. And then we're going to talk about some other things dealing with cycloaddition and these 4-pi systems, conjugated systems. All right, any questions? All right, my apologies for going over a bit.